Hello, welcome. My name is András Pályi. I work at the Budapest University of Technology and Economics in Hungary. And this lecture will be about quantum error correction with the germanium whole string qubits. In fact, the lecture consists of 3 parts. Part 1 is classical error correction, part 2 quantum error correction, and part 3 progress and challenges. So let's get started with part 1, a classical error correction. So the course is mostly about quantum computing, but here I will focus on a much simpler setup, a classical communication setup, where the goal is that we have a sender and a receiver, and the sender wants to send a single bit of information through a channel such that the receiver can also see that information. And in an ideal world, where we have ideal channels, this transmission is perfect. So if the sender sends in a 0, then the receiver receives a 0. If the sender sends in a 1, then the receiver also receives a 1. In the real world, the physical channels which are applied in such a communication situation are often noisy. And noise can take different forms, and here I'm providing an explicit numerical example of a noisy channel, which is if it's taking 0 as an input, then there is a 3% error probability, meaning that it's 3% probability that the transmitted information will be corrupted. It will be flipped from 0 to 1, actually. And in the other case, when the other input value is put in, so input is 1, then on the output we have an 8% error probability, because in 8% of the cases, this 1 will be transformed into a 0, which is an error due to the physical noises in the setup. Now, there is a very easy classical way to fight noise with the repetition code. So the repetition code is essentially error correction based on redundancy. So in this situation, the sender still wants to send only 1 bit of information, but he copies that 1 bit into 3 copies and actually sends those 3 copies through this noisy channel, the same noisy channel as we have seen before. Now, I have done this very simple probability theory calculation of what is the probability of each of the 8 possible output bit strings received by the receiver. And then you see that essentially in this error model, all 8 possibilities have a finite probability. Now, of course, this redundant way of encoding the information is useful in the sense that even if there is a bit flip happening in this noisy channel, if it's only 1 bit flip, then that means that in the received bit string, only one 0 will be flipped into 1, and the other zeros will remain there. So the receiver can use a very simple majority vote, looking into the bit string which came out of the channel, and then construct the inferred bit value by doing a majority vote of the bit values that arrived. And so I've done this simple calculation for you about the probabilities of these different output bit strings. And if the receiver uses this majority vote, that means that he will make an error only if at least 2 bit flips happened. So only if the received bit string is 110, 101, 011, or 111. I can add up all these 4 error probabilities, and I end up with 0.24% error for this scheme. 0.24% is much smaller than the 3% bit flip probability for this noisy channel. So in that sense, this repetition code does work. It does reduce the error in transmission. We can also do the same exercise for the case when the input bit is 1. So then this 1 is copied in 3 different copies, and then all 3 copies are sent through the same noisy channel. If we do this error analysis, it turns out that with the majority vote scheme, the error we have at the end is 1.5%, and this has to be compared with the 8% error probability on the previous slide. Again, this is a significant reduction of that 8%. So this repetition code indeed functions. It indeed helps fighting noise effects. Now, implicitly, I was already using the concept of the decoder in the previous slide. The decoder I was referring to is the so-called majority vote decoder. But in general, of course, you can have many ways to infer the bit value from the bit strings which you received, and the majority vote is just one option. So in error correction, classical or quantum error correction, the concept of decoder is quite important and appears often. The decoder in general is the function mapping the output bit string to the inferred bit. So in this case, this particular function was the majority vote, but one can envision other functions as well. And actually, there are certain physical situations when the majority vote decoder is not optimal, it's not the best choice, but some other decoder is performing better. Speaking about performance, of course, we also want to quantify somehow the quality of an error correction scheme. And typically, the quantification of the performance is not unique. So you can use different measures, different figures of merits to quantify the performance. And I'm just exemplifying this degree of freedom here. Performance measure is not unique in general. So for example, in this particular situation, we can define performance measure number 1 as the maximum error over the inputs. So in our case, in the previous numerical example, we had 1.5% for one of the inputs and 0.25% for the other input. So the maximum error in this case is the maximum of these two numbers, which is 1.5%. Or we could also define an alternative performance measure, measure number 2, the average error over inputs, when I just take the numerical average of the two error probabilities from the previous side. And in this case, this is going to be 0.875%. So there are usually different figures of merits which we can use to quantify the performance of such a decoder. Now, what I presented here is really the most simple classical error correction scheme. And there are many different directions along which we can generalize this idea. And let me just go through this list of possible directions here. So first of all, in the previous example, we used redundancy based on 3 bits. Of course, we can also generalize this idea to more bits. And this generalization leads to the concepts of code size. How many bits do I use to redundantly encode the single bit? And also code distance. How many errors, what is the level of protection of the error correction scheme? How many errors can we correct with the error correction scheme? Another important feature so far was that we were considering classical bits. Of course, this course is about quantum computing, so it's an interesting and important generalization to go to quantum bits, and that's going to happen in part 2 of this lecture. Also, I was assuming so far perfect initialization at the sender side, also perfect readout on the receiver side. In a quantum computing setting, often we also assume perfect gates. But of course, this is an idealized model, and to be able to connect to reality, we typically need more realistic descriptions. And this will lead to a notion of fault tolerance and fault-tolerant quantum computing. Finally, so far I was discussing a very simple communication scenario, a information transmission scenario. There are more complicated and more interesting scenarios. For example, when I want to have a memory which is error corrected, meaning that it's composed of a number of physical bit elements, and using an active error correction scheme, we want to prolong the lifetime of this memory. So that's a further step of generalization. And finally, when we want to combine these memory functionality also with computing, that's one more step of sophistication. Before I end this first part of the lecture, let me bring in 2 important concepts which also appear very often in classical and quantum error correction. And these are break-even point and error threshold. So the first one, break-even point. For a fixed code size, what is the physical error level below which the logical bit is useful? That is, it is better than the physical bit. So this concept is depicted on the right-hand side. So here you see a graph where on the x-axis you see the physical error probability. So you take a single bit, and in a simplified error model, it could be characterized by a single error probability, and that is p physical. And then on the y-axis, you see p logical, which is the error probability associated to the error correction scheme which we are using. And of course, a special line on this parameter diagram is this dashed orange line here. If our error correcting scheme is producing a point, corresponds to a point below this line, that means that the physical error is bigger than the logical error, meaning that the logical error is small. So that's the case when the error correction scheme is really useful, when it works, when it makes sense to use the encoding. If the operation corresponds to a point in this upper triangle, that means that it doesn't make sense to use that error correction scheme, because the logical error becomes bigger than the physical error. And often, when we look into classical error correction schemes, then we can compute a curve which describes how the logical error probability depends on the physical error probability. And such a typical curve is shown as the black curve here. And you see that if the physical error probability is small enough, then this black curve is going below the orange curve, which means good. It means that indeed it makes sense to use this error correction scheme in that regime. But this curve goes above the orange curve. The black curve goes above the orange curve for larger physical error probabilities, which means that if the physical error probability is too big, then it doesn't make sense to use this kind of error correction scheme. And the separation point, the critical point between the two, denoted by this purple star, is called the break-even point in this context. And the second important concept is the error threshold, which is the answer for the following question. What is the physical error level below which a large enough code ensures an arbitrarily small logical error? So this is further illustrated in this bottom right plot, where we have the same two axes as before. So we have the physical error probability axis here, and also we have the logical error probability axis here. But now there's an extra dimension appearing, and this is the code size n, which means how many bits do we combine for the error correction scheme to represent a single bit. And again, the curves which you see, so the green curve and the red curve, they represent typical behavior of certain error correction schemes. So the typical behavior is often that if the physical error probability is below some threshold, and this is called the error threshold in this context, then if we increase the code size, then we get better and better error correction scheme, because the logical error probability is decreasing with increasing code size. So that's favorable. That's when it makes sense to scale up the error correction scheme, because it will imply a reduced logical error. But if the physical error is above this error threshold, then you see a qualitatively different behavior, when by increasing the code size, actually the logical error probability is getting larger and larger. So this is the parameter region where it doesn't make sense to scale up the error correction scheme. All right, so with these concepts, important concepts, let me conclude the first part, which was about classical error correction. And in the next video, I will talk about quantum error correction.